Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere most people never think to look, even though it hangs there in our sky, visible to human eyes since the very first moments our ancestors gazed upward and wondered. I want to take you on a journey inward, toward the sun, to a small world that has been keeping secrets for billions of years. Find yourself a comfortable position now, let your shoulders drop, let your breathing begin to slow, and allow your mind to drift with me across the vast and quiet distances of space. There is no hurry here. There is only wonder, only gentle curiosity, and the soft unfolding of cosmic mysteries that have waited patiently for us to discover them. Tonight, we're going to explore something remarkable, something that puzzled scientists for decades and only recently began to reveal its secrets. We're going to talk about Mercury, the smallest planet in our solar system, the closest world to our sun, and perhaps the strangest neighbor we have ever tried to understand. And specifically, we're going to explore a mystery that seems almost impossible when you first hear it. Mercury, a planet bathed in more sunlight than any other world we know, has a surface that absorbs light like nothing else in our solar system. It is darker than it should be, stranger than we expected, and the reason why is one of the most beautiful scientific discoveries of recent times. It is a question that might seem simple at first, almost too simple to matter. Why is Mercury so dark? And yet, as we will discover together tonight, this question opens doorways into the deepest history of our solar system, into the very nature of matter itself, and into the profound connections that link all worlds, all elements, all existence in ways we're only beginning to appreciate. What if the darkness of Mercury was not a flaw or an anomaly, but a signature, a message written in carbon and time, telling us stories about the birth of planets and the patient accumulation of cosmic material over billions of years? Before we journey too far, I want to thank you for being here. If you love these cosmic journeys, these peaceful explorations of the universe's mysteries, perhaps you might consider pressing the like button, and if you have not already, subscribing to join us for future voyages through the stars. And I'm curious about you tonight. Where are you watching from? What corner of our beautiful Earth holds you as you listen to these words? And what time is it there? Is it late evening, with the day's activities finally settling into quietness? Is it the deep middle of the night when the world outside your window has grown still and the stars are wheeling slowly overhead? Or perhaps it is some other hour entirely, a moment you have carved out for yourself to simply rest and wonder. Whatever time it is, wherever you are, you're welcome here, and we will travel together through these mysteries at whatever pace feels right. Now, let us begin to consider Mercury, this small world that orbits so close to our sun. To truly appreciate the mystery we're exploring tonight, we need to first understand just how remarkable Mercury's situation is in our solar system. Imagine, if you will, being so close to the sun that its light is nearly 7 times more intense than what we experience here on Earth. Imagine a world where the sun does not appear as the modest golden disk we see in our skies, but as an enormous blazing presence, 2.5 times larger than what we know, dominating the heavens with overwhelming brilliance. This is Mercury's reality, a world bathed in light so intense that the temperatures on its sunlit side can reach over 400 degrees Celsius, hot enough to melt certain metals, hot enough to make the very rocks glow with absorbed heat. And yet here is where our mystery begins to take shape. Despite receiving all of this incredible sunlight, despite being illuminated more intensely than any other planet in our solar system, Mercury's surface is remarkably dark. When scientists first began studying Mercury closely, they expected to find a world that reflected light quite efficiently, a bright surface glinting in the solar glare. What they found instead was something puzzling, something that did not match their predictions at all. Mercury reflects only about 10% of the light that falls upon it. To put this in perspective, our own moon, which seems so bright and luminous in our night sky, reflects about 12% of the sunlight it receives. Mercury, despite being so much closer to the sun, despite being bathed in so much more light, is actually darker than our moon. This might seem like a small detail, a minor astronomical curiosity not worth losing sleep over, and yet in science, it is often these small anomalies, these gentle deviations from what we expect, that lead us to the most profound discoveries. The darkness of Mercury whispered to scientists that something unusual was happening on that distant surface, something that required explanation, something that held secrets about the very nature of planetary formation and evolution. Let your mind drift now across the 90 million kilometers that separate us from Mercury at its closest approach. Feel yourself floating through the vacuum of space, where there is no sound, no wind, only the patient streaming of sunlight outward from our star and the gentle pull of gravity shaping the movements of all things. In this vast quietness, Mercury traces its path around the Sun, a small grey world moving faster than any other planet, yet taking its time, keeping its secrets, waiting for us to develop the technology and the curiosity to come closer and ask our questions. What makes Mercury so special, so different from the other rocky worlds we know? Part of the answer lies in its location, that precarious orbit so close to the Sun's gravitational embrace. Mercury exists in a realm of extremes that we can barely imagine from our comfortable position here on Earth. The temperature differences on this small world are the most dramatic in our solar system. While the side facing the Sun bakes at over 400 degrees, the side facing away, the long night side, plunges to temperatures below negative 170 degrees Celsius. This is a range of nearly 600 degrees, a swing from conditions that would instantly destroy any spacecraft we could build to conditions colder than any natural environment on Earth. And yet, despite these violent extremes, there is something peaceful about Mercury when we view it from afar. It moves through its orbit with mathematical precision, following the laws of physics that govern all motion in our universe. It rotates slowly, so slowly that a single day on Mercury, measured from one sunrise to the next, lasts 176 Earth days. Imagine watching the sun rise on Mercury, seeing it climb slowly, so slowly into that black sky, taking weeks to reach its highest point, then beginning its equally leisurely descent toward the horizon. Time moves differently there, or rather, our perception of time would be utterly transformed by Mercury's patient rotation. This slowness is itself a mystery worth contemplating. Mercury is tidally locked with the Sun in a peculiar way, caught in what scientists call a 3-to-2 spin-orbit resonance. For every 2 orbits Mercury makes around the Sun, it rotates exactly 3 times on its axis. This creates a dance of incredible precision, a gravitational relationship that has been maintained for billions of years. There is something almost hypnotic about imagining this dance, this slow, eternal waltz between a small planet and its overwhelming stellar partner. As you lie there listening, perhaps feeling the weight of your body settling more deeply into whatever surface supports you, consider how Mercury has been performing this dance since long before life existed on Earth. When the first simple cells were forming in our ancient oceans, Mercury was already old, already spinning in its careful rhythm, already hiding its dark secrets beneath a surface that had been formed and reformed by cosmic processes we are only now beginning to understand. There is comfort in this thought, in the recognition that the universe carries on its processes with or without our awareness, that worlds continue their journeys whether or not anyone is watching. Now, the darkness of Mercury presented scientists with a genuine puzzle, one that required careful investigation and creative thinking to solve. When we look at other rocky bodies in our solar system, we can usually explain their colours and brightness by understanding what materials make up their surfaces. The Moon, for example, is covered in a layer of fine, rocky debris called regolith, created by billions of years of meteorite impacts grinding the surface into powder. This material reflects light in predictable ways based on its mineral composition. Mars is red because of iron oxide, rust essentially, coating its rocks and dust. The bright patches on some asteroids come from specific minerals that reflect light efficiently. But Mercury did not fit neatly into these explanations. Its surface seemed to be made of similar materials to our Moon, the same basic kinds of silicate rocks and minerals, and yet it was significantly darker. Something was coating Mercury's surface, something was absorbing the light, and for many years, scientists could only speculate about what that something might be. One early hypothesis suggested that Mercury's darkness came from space weathering, the gradual alteration of surface materials by the constant bombardment of solar wind and micrometeorites. This process is known to darken surfaces over time, and Mercury, being so close to the Sun, would experience space weathering more intensely than any other world. This seemed like a reasonable explanation, and for a while many scientists accepted it as the likely answer. But as measurements became more precise, as our instruments grew more sophisticated, it became clear that space weathering alone could not account for just how dark Mercury really was. Something else was going on, something additional, something that required a different explanation entirely. Let us pause here for a moment and appreciate the process of scientific discovery that we are witnessing in this story. Science is not a sudden flash of insight, not a single moment of revelation. It is a slow, patient accumulation of observations, hypotheses, tests, and revisions. Scientists looked at Mercury and saw something unexpected. They proposed explanations that seemed reasonable. They tested those explanations against further observations, and when the explanations fell short, they did not give up or pretend the problem was solved. They kept looking, kept questioning, kept wondering. There is something deeply human in this process, and something deeply beautiful. We are creatures who cannot leave mysteries alone. We must understand, and we will keep trying until we do. The breakthrough in understanding Mercury's darkness came, as so many breakthroughs do, from a combination of new technology and creative thinking. But before we explore that discovery, we need to understand more about Mercury itself, more about its contradictions and peculiarities, more about why this small world continues to fascinate and puzzle us. For Mercury is not just dark, it is strange in almost every way we can measure, a world of contradictions that challenges our assumptions about how planets work. Consider the density of Mercury. How much mass is packed into its small volume? Mercury is the second densest planet in our solar system, after Earth, and if you account for the compression caused by gravity, Mercury would actually be denser than our own world. This means that Mercury contains an unusually large amount of heavy elements, particularly iron. In fact, Mercury's iron core makes up about 85% of the planet's radius, a proportion far larger than any other rocky planet we know. If Mercury were the size of a grapefruit, its core would be like a solid metal ball the size of an orange inside it, with only a thin shell of rocky material forming the outer layers. This enormous core is itself a mystery. Why should the innermost planet have such an oversized metallic heart? Several theories have been proposed over the years. Perhaps Mercury once had more rocky material, but it was stripped away by a giant impact early in the solar system's history, leaving behind mostly the dense metallic core. Perhaps the intense solar radiation so close to the Sun prevented lighter materials from condensing when Mercury was first forming, leaving only the heaviest elements to accumulate. Or perhaps the processes that built Mercury were simply different from those that built the other rocky planets, driven by conditions we do not fully understand. Whatever the reason, Mercury's large core has profound implications for the planet's history and current state. That core is still partially liquid today, something scientists discovered through careful measurements of Mercury's rotation. A completely solid planet would wobble differently than one with a liquid layer inside, and Mercury wobbles in a way that tells us something inside is still molten, still flowing, even after 4.5 billion years. There is something remarkable about this, something worth holding in your mind as you rest. Deep inside this small, sun-scorched world, metal is still flowing, still moving, still carrying heat from the deep interior toward the surface. Mercury is not a dead world, not completely. Something is still happening inside. As you settle more deeply into relaxation, let your breathing continue to slow, and consider how different Mercury is from what we might naively expect. We might think that a small planet so close to the Sun would be simple, would be thoroughly cooked and sterilized and uniform. But the universe does not work that way. Complexity arises everywhere we look. Mystery hides in every corner, and the more closely we examine any object in space, the more questions we find waiting for us. This is not frustrating, not if we approach it with the right spirit. This is wonderful. This means that wonder will never run out, that there will always be more to discover, more to contemplate, more to hold in our minds as we drift towards sleep. Mercury's magnetic field adds another layer to its contradictions. By all rights, Mercury should not have a significant magnetic field at all. The generation of planetary magnetic fields requires a liquid, electrically conducting layer that can flow and generate electrical currents. Most small rocky bodies cooled long ago and lost whatever magnetic fields they once had. Mars, for example, has only the remnants of an ancient magnetic field, locked into its rocks like a geological memory, but no active field being generated today. Mercury is even smaller than Mars, and yet it has a global magnetic field, weak compared to Earth's but definitely present, definitely being generated by some ongoing process deep inside. This magnetic field interacts with the solar wind, that constant stream of charged particles flowing outward from the Sun, creating a small bubble of protected space around Mercury. This bubble, called a magnetosphere, is unlike any other in our solar system. It is tiny compared to Earth's massive magnetosphere, and the solar wind is so intense at Mercury's distance that the magnetic shield is constantly being compressed and distorted. Sometimes during particularly strong solar events, the magnetosphere is pushed so close to Mercury's surface that the solar wind can directly impact the planet's rocks, stripping away atoms and sending them drifting off into space. There is something poignant about imagining this process, Mercury's magnetic field fighting a constant battle against the overwhelming pressure of the Sun's output. It is a battle that Mercury cannot truly win, not in the long run. The planet loses material constantly, atoms and molecules liberated from its surface and swept away by the solar wind. Mercury has an extremely thin exosphere, not really an atmosphere at all, but a sparse collection of atoms bouncing around above the surface, constantly being lost to space and constantly being replenished by the liberation of new atoms from the rocks below. In a sense, Mercury is slowly evaporating, losing itself bit by bit to the cosmic environment. But this process is so slow, so gradual, that Mercury will remain largely intact for billions of years to come. The universe often works this way, with processes that seem dramatic unfolding over timescales so long that they become almost peaceful, almost meditative in their patience. If you're still with me now, if you're floating somewhere between waking and sleeping, I want to thank you for staying on this journey. Perhaps you might leave a comment below telling me where you're watching from, what time it is in your corner of the world, and what aspect of Mercury's story has captured your imagination so far. There is something wonderful about knowing that these words are reaching people all around our planet, that we are all looking upward together, contemplating the same mysteries, even as we rest in our separate places. And if you have not yet pressed the like button, perhaps now might be a gentle moment to do so, to let me know that these cosmic journeys matter to you, that the universe's mysteries are worth exploring together. Now, let us turn our attention to one of the most fascinating aspects of Mercury's contradictory nature, the relationship between its day and its year, between its rotation and its orbit. I mentioned earlier that Mercury is caught in a 3-to-2 resonance with the Sun, and this creates some truly bizarre effects that are worth contemplating as we drift deeper into our exploration. Mercury orbits the Sun once every 88 Earth days. This is its year, the time it takes to complete one full journey around our star. But Mercury rotates on its axis much more slowly, taking about 59 Earth days to complete one rotation. Now, if Mercury were not orbiting the Sun, this would mean that its day and night cycle would simply be 59 Earth days long. But Mercury is orbiting, and it is orbiting very quickly compared to its rotation, and this creates a complicated interaction between the two motions. The result is that a solar day on Mercury, measured from one noon to the next, lasts about 176 Earth days. This is 2 complete Mercury years. Imagine standing on Mercury's surface, watching the Sun rise. You would wait nearly 3 Earth months for it to reach its highest point in the sky, then another 3 months for it to set, then nearly 6 months of darkness before it rose again. A single day-night cycle would take almost half an Earth year. But here is where things become even stranger, because Mercury's orbit is highly elliptical, meaning it is more oval-shaped than circular, and because the planet moves faster when it is closer to the Sun and slower when it is farther away, the Sun appears to do something very strange in Mercury's sky. At certain points in Mercury's orbit, when the planet is moving fastest and closest to the Sun appears to stop in the sky, reverse direction briefly, and then continue on its way. If you were standing at certain locations on Mercury's surface, you would see the Sun rise, climb partway up the sky, then set back below the horizon where it came from, rise again, and finally continue its slow journey across the sky. This retrograde motion of the Sun is one of the most alien phenomena in our solar system, something that happens nowhere else that we know of. It is a consequence of Mercury's particular combination of orbital and rotational characteristics, a cosmic accident that creates an experience utterly unlike anything possible on Earth. There is something dreamlike about imagining this, something that suits our journey towards sleep. A sun that rises, changes its mind, sets again, and then rises once more. As if the universe itself were caught in a moment of contemplation, a pause between one state and the next. Mercury's surface, where this strange sun would be observed, is itself a testament to billions of years of cosmic history. Like our moon, Mercury is covered with impact craters, the scars of countless collisions with asteroids and comets over the eons. Some of these craters are enormous, basins hundreds of kilometers across that formed when particularly large objects slammed into Mercury with tremendous force. The largest of these, the Caloris Basin, is one of the most impressive impact structures in the entire solar system. A scar more than 1,500 kilometers in diameter, so large that it could swallow several European countries with room to spare. The formation of the Caloris Basin was a violent event, an impact so powerful that it sent shockwaves through Mercury's entire interior. On the exact opposite side of the planet from the impact site, scientists have found a region of bizarre, chaotic terrain, where hills and depressions are jumbled together in a confused landscape. This terrain is thought to have been created when the shockwaves from the Caloris impact travelled through Mercury, converging on the far side and disrupting the surface. Imagine the energy required to shake an entire planet like that, to create geological chaos on the far side of a world through the sheer force of an impact on the near side. And yet, despite this violent history, Mercury today is a quiet place. The heavy bombardment that created these craters ended billions of years ago as the solar system settled into its current, more stable configuration. Now, Mercury simply circles the Sun, patient and silent, its surface a record of ancient violence that has long since faded into peace. The craters remain, but the forces that created them are largely absent now. This is true of much of the solar system. The violence of formation has given way to the quiet of maintenance, the slow, steady processes that now govern the movements and evolution of worlds. As we continue to explore Mercury's nature, we find ourselves returning again and again to that central mystery. Why is this world so dark? We have established that Mercury receives more sunlight than any other planet, that its surface should, by simple logic, appear bright and reflective. We have noted that scientists expected one thing and found another, that Mercury's darkness was an anomaly requiring explanation. Now, let us begin to explore the observations and discoveries that eventually led to understanding. The key instrument in solving this mystery was a spacecraft, a robotic explorer sent from Earth to study Mercury up close. Before this spacecraft arrived, our knowledge of Mercury was limited to what we could observe from Earth and from brief flybys by earlier missions. The Mariner 10 spacecraft flew past Mercury 3 times in the mid-1970s, giving us our first close-up views of about half of Mercury's surface. Those images revealed a cratered world similar in appearance to our Moon, but they could not tell us everything we needed to know. Many questions remained, including the question of Mercury's darkness. For decades after Mariner 10, no spacecraft visited Mercury. The planet is actually quite difficult to reach, not because it is far away, but because it orbits so close to the Sun. A spacecraft travelling toward Mercury must fight against the Sun's gravity, while simultaneously avoiding falling into the Sun itself. This requires complex orbital maneuvers, multiple flybys of other planets to adjust speed and trajectory, and a great deal of patience. The journey to Mercury is not a straight line, but a careful spiral, a dance with gravity that takes years to complete. But eventually, after years of planning and development, a new mission was approved. This mission would carry sophisticated instruments capable of measuring Mercury's composition, mapping its surface in unprecedented detail, and solving mysteries that had puzzled scientists for decades. The spacecraft was called MESSENGER, an acronym that stood for Mercury's surface, space environment, geochemistry, and ranging. It launched in August of 2004 and began its long journey toward the innermost planet. The journey took nearly 7 years. Messenger flew past Earth once, Venus twice, and Mercury itself 3 times, before finally settling into orbit around the planet in March of 2011. Each flyby provided gravitational assists that adjusted the spacecraft's trajectory, gradually bringing it closer to the complicated orbital parameters needed to orbit Mercury. During the Mercury flybys, Messenger gathered data and images, giving scientists their first new close-up views of the planet in over 30 years. But the real work would begin once the spacecraft was in orbit, able to study Mercury continuously for an extended period. Messenger operated in Mercury orbit for more than 4 years, far exceeding its original mission plan. During that time, it mapped the entire surface of Mercury in high resolution, measured the composition of surface rocks using spectrometers, studied the planet's magnetic field and thin exosphere, and gathered data that transformed our understanding of this small, strange world. It was Messenger data that finally allowed scientists to explain why Mercury is so dark, to solve the mystery that had puzzled observers for so long. But before we reveal that explanation, let us stay with Messenger for a moment longer. There is something moving about contemplating this spacecraft's journey and fate. Messenger traveled billions of kilometers through space, spent years in the harsh environment around Mercury, endured temperature extremes and radiation exposure that would destroy most human-made objects, and faithfully transmitted its observations back to Earth. In the end, with its fuel exhausted and its orbit decaying, Messenger crashed into Mercury's surface on April 30th, 2015, creating a new small crater on the planet it had studied for so long. In a sense, Messenger became part of Mercury, its remains joining the ancient rocks and dust that cover the planet's surface. The atoms that made up the spacecraft, forged in factories on Earth from elements that were themselves forged in ancient stars, now rest on a world 90 million kilometers from home. There is a poetry in this, a reminder that everything in the universe is connected, that matter flows from place to place over cosmic timescales, that nothing is ever truly lost, only transformed and redistributed. As you lie there, perhaps feeling your thoughts beginning to drift and soften, consider the journey that Messenger made and the knowledge it brought back to us. We send these robotic extensions of ourselves out into the cosmos, these machines that carry our curiosity and our questions, and they return with answers we could never have found without them. It is one of the most remarkable things our species does, this reaching outward, this refusal to accept that some things are simply too far away to understand. Now, the data from Messenger told scientists many things about Mercury, but one of the most surprising discoveries related directly to our mystery of the planet's darkness. When scientists analyzed the composition of Mercury's surface using Messenger's instruments, they found something unexpected. The surface contained significantly more carbon than similar analyses had found on the Moon or other rocky bodies, and not just any carbon, but carbon in a particular form, graphite. Graphite is a familiar substance here on Earth. It is what makes pencils write. A soft, dark material composed of carbon atoms, arranged in sheets that slide easily over one another. On Earth, graphite forms under specific conditions of heat and pressure, often associated with metamorphic rocks that have been subjected to intense geological processing. But on Mercury, the graphite appeared to be everywhere, mixed into the surface material in quantities sufficient to significantly darken the entire planet. This was a remarkable finding, but it raised immediate questions. Where did all this carbon come from? How did it get spread across Mercury's surface? What processes could have distributed graphite so evenly across an entire world? The answers to these questions would lead scientists deeper into Mercury's history than they had ever gone before, back to the very formation of the planet itself, back to a time when Mercury was not the solid, cratered world we see today, but something far more dynamic and strange. Let us pause here and acknowledge the wonder of this discovery. For years, scientists had noticed that Mercury was darker than expected, and had struggled to explain why. The answer turned out to be carbon, one of the most common elements in the universe, an element that forms the basis of all life on Earth, an element that was present in the cloud of gas and dust that gave birth to our entire solar system. The darkness of Mercury is not a flaw or an anomaly, but a signature of cosmic chemistry, a record of processes that shaped this world billions of years ago. And now, as we prepare to explore more deeply how this carbon came to coat Mercury's surface, I want to invite you to sink even more deeply into relaxation. We have travelled far together already, from the warmth of wherever you are resting to the sun-scorched surface of the innermost planet. We have contemplated Mercury's contradictions, its slow rotation and fast orbit, its massive core and strange magnetic field, its ancient craters and bizarre solar phenomena. We have followed Messenger on its 7-year journey and mourned its eventual end on the world it had come so far to study. And we have begun to glimpse the answer to our central mystery, the carbon that darkens Mercury's ancient surface. There is much more to explore, much more to wonder about. The story of Mercury's carbon is not simple, but layered, involving multiple processes unfolding over different timescales. Some of the carbon fell from above, carried by comets and asteroids that have been bombarding Mercury since the solar system was young. Some of it rose from below, emerging from the planet's interior during volcanic eruptions that once reshaped the surface. And some of it may have been there from the very beginning, incorporated into Mercury's rocks during the planet's initial formation, and then brought to the surface through processes we are only beginning to understand. As we drift now from the puzzle of Mercury's darkness into the exploration of where that darkness came from, let your mind float on these possibilities like a boat on a gentle sea. There is no rush to reach any destination. The journey itself is the purpose, the contemplation of cosmic mysteries that stretch back billions of years and span millions of kilometers. In the quiet of space, where Mercury circles endlessly around our Sun, time moves differently than it does here. Billions of years are just another orbit, another slow rotation, another patient accumulation of carbon atoms falling from the sky. And perhaps, as you rest, you might consider the carbon in your own body, the atoms that form your muscles and bones and brain. That carbon too came from somewhere, was forged in the hearts of ancient stars and scattered through space by stellar explosions. The carbon in you and the carbon on Mercury share a common origin, a cosmic heritage that connects all matter in the universe. You're not separate from the mysteries we're exploring tonight. You're made of the same stuff, shaped by the same processes, part of the same vast story of matter and energy unfolding over cosmic time. There is something peaceful in this recognition, something that can help quiet the mind as sleep approaches. We are small, yes, vanishingly small compared to the scale of the universe. But we are also connected, woven into the fabric of everything that exists. The questions we ask about Mercury are questions about ourselves, about where we came from, and what our place is in this vast cosmos. And the answers, when they come, remind us that we belong here, that we are part of something ancient and ongoing and full of wonder. Let us continue now, drifting deeper into the story of Mercury's carbon and the extraordinary history it reveals. The discovery that Mercury's surface is rich in graphite was just the beginning. Scientists then had to figure out how that graphite got there, and the explanations they developed take us on a journey through time, back to the earliest days of our solar system and the violent processes that formed the planets we know today. One source of Mercury's carbon is external, coming from objects that fall onto the planet from space. Throughout its history, Mercury has been bombarded by comets, asteroids, and smaller debris, just like every other body in the solar system. Many of these impactors contain carbon-rich materials, the same primordial compounds that have been present in the solar system since its formation. When these objects strike Mercury's surface, they deliver their carbon to the planet, adding to the material that covers the ground. This process has been going on for billions of years, ever since Mercury first formed. In the early solar system, when there was much more debris flying around, the bombardment was particularly intense. Mercury, like our Moon and Mars and every other rocky body, was subjected to what scientists call the Late Heavy Bombardment, a period about 4 billion years ago when impact rates were far higher than they are today. During this time, countless carbon-rich objects would have struck Mercury, adding their material to the surface layer. But external delivery alone cannot explain the amount and distribution of carbon on Mercury. If carbon were only coming from impactors, we might expect to find it concentrated around impact sites, in the floors and walls of craters where the infalling material had been deposited. Instead, the carbon appears to be distributed more evenly, spread across the surface in a way that suggests additional processes at work. This is where the story becomes even more fascinating. because the additional process appears to involve Mercury's own interior, the deep layers of the planet that have been largely hidden from our view. Scientists now believe that much of Mercury's surface carbon rose from below, emerging from the planet's depths through geological processes that unfolded when Mercury was young. To understand this, we need to go back in time, far back to the moment of Mercury's formation. When Mercury first came together from the cloud of gas and dust surrounding the young sun, it was not the solid, rocky world we see today. The energy of formation, the heat from countless collisions, and the pressure of gravity pulling everything together was so intense that much of Mercury would have been molten. The planet would have been covered, perhaps entirely, by an ocean of liquid rock, a magma ocean that glowed red and orange against the blackness of space. This magma ocean phase is thought to be common in the formation of rocky planets. Earth went through it, the Moon went through it, Mars went through it. The intense heat of formation melts the rocky material, creating a liquid layer that can be hundreds of kilometers deep. Over time, as the planet radiates heat into space, this magma ocean gradually cools and solidifies, forming the crust and mantle that we see today. But here is where Mercury's story diverges from what happened on other worlds. When a magma ocean cools, different materials crystallize at different temperatures. Heavier materials tend to sink toward the bottom, while lighter materials tend to float toward the top. This process, called fractional crystallization, is what separated Mercury's enormous iron core from its rocky mantle, as the dense iron-rich liquid sank toward the planet's center. And what about carbon? Carbon, in the form of graphite, is actually quite light compared to the silicate minerals that make up most rocky material. In a magma ocean containing dissolved carbon, as the magma began to cool and crystallize, the graphite would have floated upward, rising through the liquid rock like bubbles in a glass of water. This graphite would have accumulated at the surface, forming a layer of carbon-rich material on top of the solidifying planet. This is an extraordinary image to hold in your mind as you rest. Billions of years ago, on the small world closest to our sun, a planet-wide ocean of liquid rock slowly cooled and solidified. As it did, flakes of graphite floated upward through the glowing magma, drifting toward the surface like a kind of cosmic snow falling in reverse, rising instead of falling, dark flakes ascending through orange light to settle on the cooling surface above. This process may have taken millions of years, a slow and patient accumulation of carbon at the boundary between rock and space. The graphite layer that formed in this way would have been Mercury's original crust, or at least a significant component of it. This primordial carbon-rich surface was then subjected to billions of years of bombardment, volcanic activity, and space weathering, mixing and redistributing the carbon across the entire planet. What we see today, the dark surface that absorbs sunlight so efficiently, is the legacy of this ancient process, a memory of Mercury's magma ocean preserved in the very rocks that cover the surface. There is something deeply satisfying about this explanation, the way it connects Mercury's present darkness to events that occurred at the very beginning of the planet's history. The carbon we observe is not new, not recently delivered, but ancient beyond imagining, a remnant of a time when Mercury was still forming, still differentiating, still sorting itself into the layered structure we can measure today. When you look at Mercury in the sky, when you see that small point of light moving against the background of stars, you are seeing a world painted in carbon that rose from primordial depths 4.5 billion years ago. And now, if you're still with me, still floating somewhere between waking and sleeping, I want to invite you to pause and consider what you have found most interesting in our journey so far. Perhaps it is the strange behavior of the sun in Mercury's sky, that rising and setting and rising again. Perhaps it is the enormous core of iron that makes up most of the planet's interior. Perhaps it is the image of graphite floating upward through an ocean of molten rock, a planet-wide process of cosmic crystallization. Whatever has captured your imagination, I would love to hear about it. Leave a comment below and tell me what aspect of Mercury's story speaks to you. These small connections between us, these moments of shared wonder, are part of what makes these journeys meaningful. Let us now go deeper still into the evidence for Mercury's carbon-rich surface, exploring the observations and analyses that confirmed what Messenger had discovered. Science is not just about having ideas, but about testing them, about gathering evidence and checking whether reality matches our expectations. The story of Mercury's carbon is supported by multiple lines of evidence, each one adding weight to the explanation we have been exploring. The primary evidence came from Messenger's neutron spectrometer, an instrument designed to measure the composition of planetary surfaces by detecting the particles released when cosmic rays strike the ground. When high-energy particles from space hit a planet's surface, they knock loose neutrons from the atoms in the rocks. These neutrons bounce around, colliding with other atoms, and some of them escape back into space where they can be detected by orbiting spacecraft. The energy and number of these neutrons depends on what elements are present in the surface, because different elements interact with neutrons in different ways. Carbon, in particular, is very effective at slowing down neutrons, absorbing their energy through multiple collisions. A surface rich in carbon will produce fewer high-energy neutrons and more low-energy neutrons than a surface poor in carbon. By measuring this neutron energy distribution, scientists can estimate how much carbon is present in the surface material. Messenger's measurements showed clearly that Mercury's surface contains more carbon than similar measurements have found on the Moon or other rocky bodies. The concentration was highest in the oldest, most heavily cratered regions of the planet, exactly where we would expect to find remnants of Mercury's original, carbon-rich crust. Younger regions, formed by volcanic activity after the original crust had formed, showed lower carbon concentrations, consistent with lava that had welled up from beneath the graphite layer. This pattern, high carbon in old terrain and lower carbon in volcanic terrain, provided strong support for the magma ocean hypothesis. If the carbon had come primarily from external sources, from impacting comets and asteroids, we would expect to see a different distribution, perhaps higher concentrations in some of the larger impact basins where more material would have been delivered. Instead, the distribution matches what we would expect if the carbon had been present from the beginning, concentrated in the original crust and then partially buried or replaced by later volcanic activity. Additional support came from analysis of specific features on Mercury's surface. Scientists identified regions where the carbon concentration was particularly high, and these regions corresponded to areas with distinctive spectral properties, meaning they reflected light in characteristic ways that could be measured by Messenger's cameras and spectrometers. These carbon-rich regions appeared dark even compared to their surroundings, creating patches of deeper darkness against the already dark surface. Some of the most carbon-rich spots were found in and around craters in the material that had been excavated from below the surface by impacts. This excavated material, called ejecta, would include rock from deeper layers that had been buried by billions of years of surface processes. If the carbon-rich original crust had been covered by later volcanic deposits, then impacts that dug through those deposits would bring the underlying carbon-rich material back to the surface. And indeed, some of the darkest material on Mercury is found in exactly these locations, in the floors and walls and ejecta blankets of craters that penetrated deep enough to reach the ancient carbon layer. There is something elegant about this confirmation, the way multiple observations from different instruments point toward the same conclusion. The neutron spectrometer says there is carbon. The spectral measurements say there is graphite. The distribution pattern says the carbon is ancient, part of Mercury's original crust. The crater ejecta says the carbon is buried beneath later deposits, preserved at depth, and brought back to the surface by impacts. Each piece of evidence fits together with the others, building a coherent picture of Mercury's history and composition. But science is never satisfied with a single explanation, no matter how well supported. Scientists always look for alternative possibilities, other ways to interpret the data, other processes that might produce similar results. In the case of Mercury's carbon, researchers considered several alternatives before settling on the magma ocean hypothesis as the most likely explanation. One alternative was that all the carbon came from external sources, from the accumulated debris of billions of years of impacts. This idea could not be completely ruled out, but it struggled to explain the distribution of carbon, why it would be concentrated in the oldest terrains rather than in impact basins where external material would have been deposited. It also struggled to explain the total amount of carbon present, which seemed higher than external delivery alone could easily account for. Another alternative suggested that the carbon might have been produced on Mercury's surface through chemical reactions driven by the solar wind. The intense stream of particles from the sun, constantly bombarding Mercury's surface, could potentially create carbon compounds through interactions with other surface materials. But this process would also be expected to operate more intensely in some regions than others, and it could not easily explain the pattern of carbon distribution that was actually observed. A third alternative proposed that the carbon might have been delivered by a single large impact, a massive comet collision that deposited a global layer of carbon-rich material. This idea was appealing in some ways, as it could explain how carbon got distributed across the entire surface, but it struggled to explain why the carbon concentration would be highest in the oldest terrains and lowest in the volcanic regions, a pattern that requires the carbon to have been present before the volcanic activity occurred. In the end, the magma-ocean hypothesis provided the best fit to all the available evidence. It explained the total amount of carbon, its distribution across the surface, its relationship to terrain age, and its presence in excavated crater material. It also connected Mercury's darkness to a process, magma-ocean crystallization, that is thought to be common in the formation of rocky planets, making it geologically plausible as well as consistent with the observations. This is how science works at its best, not by accepting the first explanation that comes along, but by testing multiple possibilities against the evidence and selecting the one that fits best. The story of Mercury's carbon is a story of careful investigation, of instruments sent across the solar system to gather data, of scientists analyzing that data and debating its meaning, of alternative hypotheses proposed and tested and refined until the most likely explanation emerged. And now, as we prepare to continue our journey deeper into Mercury's mysteries, let your mind settle into the peace of knowing that understanding is possible, that the universe, for all its vastness and strangeness, can be comprehended through patient investigation and creative thinking. The darkness of Mercury, once a puzzle, is now a story, a narrative that connects the present state of the planet to processes that occurred billions of years ago. And this story, like all good stories, opens up new questions even as it answers old ones. For example, if Mercury's original crust was rich in graphite, what happened to that crust over the billions of years since it formed? We know that Mercury has experienced extensive volcanic activity, with lava flows covering large portions of the surface and creating the smooth plains that alternate with the heavily cratered highlands. Did this volcanic activity bury the original carbon-rich crust? If so, how much of it remains accessible near the surface, and how much has been deeply buried beneath kilometers of volcanic rock? We also wonder about the carbon that continues to arrive from space, the ongoing delivery of material by comets and asteroids. How does this external carbon interact with the ancient carbon already present? Does it add significantly to the surface inventory, or is it a minor contribution compared to what was there from the beginning? And how does the intense space weathering environment near the Sun affect the carbon over time, breaking down some forms and creating others? These questions await future missions, future instruments, future generations of scientists who will continue the work that Messenger began. For now, we can rest in what we have learned, appreciating the progress that has been made while acknowledging how much remains to be discovered. This is the nature of science, this endless frontier of questions beyond questions, each answer revealing new mysteries to explore. As we drift now toward the midpoint of our journey, having explored Mercury's nature and the discovery of its carbon-rich surface, we find ourselves ready to examine more closely the specific mechanisms that brought this carbon to where we can detect it today. The next phase of our exploration will take us through the details of how comets and asteroids delivered their carbon payloads, how Mercury's ancient magma ocean might have functioned, and how these processes have left their signatures in the features we can observe today. But for now, let us simply rest in the wonder of what we have already discovered. Mercury, that small point of light visible in our morning and evening skies, is a world with a story to tell. Its darkness speaks of ancient processes, of carbon accumulating over billions of years, of a planet that formed in violence and settled into the quiet patience of a world orbiting endlessly around its star. In the graphite that coats its surface, we can read the history of our solar system, the chemical processes that shaped the worlds we know, and the connections that link all matter across cosmic distances and timescales. And you, listening to these words, are part of this story too. The atoms in your body were forged in the same stellar furnaces that created the atoms on Mercury. The carbon in your cells is related to the carbon on that distant surface, both products of the same cosmic chemistry that has been operating since the universe began. When you contemplate Mercury, you're contemplating yourself, your own origins, your own place in the vast and ancient universe. Let this thought be a comfort as sleep approaches. You're not alone in the cosmos, but connected to everything that exists, linked by bonds of matter and energy and time that span billions of years and billions of light years. The mysteries we explore are not abstract curiosities, but intimate truths, revelations about the nature of reality and our place within it. Rest now in this connection, in this belonging, and let the gentle darkness of Mercury's surface be a reminder that even darkness can hold wonders. The story continues, as stories do, each chapter leading into the next with the patient inevitability of a planet orbiting its star. We have explored Mercury's nature and discovered why it is so dark. Now, we will go deeper, exploring the mechanisms in more detail, the evidence more thoroughly, the implications more fully. But there is no rush. The universe has been waiting for billions of years. It can wait a little longer while we rest and gather our strength for the journey ahead. Perhaps you're still fully awake, your mind engaged with these cosmic mysteries, eager to learn more. Perhaps you're beginning to drift, your thoughts softening around the edges, the words becoming more like music than meaning. Wherever you are in this spectrum, you're exactly where you should be. This journey accommodates all states of consciousness, all levels of attention, all degrees of engagement. Whether you absorb every detail or let the words wash over you like waves on a shore, you are part of this exploration, and your presence here is valued. The carbon rain that fell on Mercury, and perhaps continues to fall even now, connects this small world to the larger story of our solar system. Comets and asteroids are messengers from the outer reaches of the solar system, carrying materials that have been preserved in the cold darkness since the very beginning. When these objects strike Mercury, they deliver not just carbon, but water ice, organic molecules, and other compounds that tell us about conditions in the solar nebula 4.5 billion years ago. Some of Mercury's carbon undoubtedly came from these messengers, these emissaries from the cold outer solar system. The comets that streak across our skies, trailing their beautiful tails of gas and dust, are repositories of primordial material, frozen samples of the solar system's earliest chemistry. When they strike a planet, they deposit this material, adding to whatever was already there, mixing the ancient with the even more ancient. Scientists have traced the carbon in carbonaceous meteorites, the rocky fragments that sometimes fall to Earth and provide samples of asteroid material for direct analysis. These meteorites contain various forms of carbon, including organic compounds of surprising complexity. Similar material would have been delivered to Mercury over billions of years, contributing to the surface inventory that MESSENGER detected. But as we discussed, external delivery alone cannot explain all the carbon on Mercury. The distribution pattern, with higher concentrations in older terrains, suggests that much of the carbon was present from the beginning, part of Mercury's original makeup rather than a later addition. This points us back to the magma ocean, to that primordial state when Mercury was still molten, and the processes of planetary differentiation were sorting material by density. The magma ocean hypothesis for Mercury's carbon is elegant in its simplicity. As the molten rock cooled and crystallized, graphite, being lighter than the silicate minerals forming around it, floated upward. This process, called flotation crystallization, is well understood from studies of igneous rocks on Earth, where similar sorting of materials by density occurs during the cooling of magma. On Mercury, the scale was simply larger, planetary rather than local, and the result was a global layer of carbon-rich material at the surface. We can imagine this process if we like, though the reality would have been beyond anything human experience could comprehend. A world covered in glowing liquid rock, red and orange and yellow, radiating heat into the blackness of space, the surface roiling and churning as convection currents move heat from the depths toward the surface. And throughout this hellish ocean, tiny flakes of graphite forming and floating upward, dark specks rising through the incandescent liquid, accumulating in a layer at the top where the magma meets the void. This layer would not have been pure graphite, of course. It would have been mixed with other materials that were also crystallizing out of the magma, forming a complex crust of various minerals with graphite as a significant component. Over time, as the magma ocean continued to cool and solidify, this crust would have thickened and hardened, eventually becoming the rigid outer layer of the planet. But Mercury's geological activity did not end with the solidification of the magma ocean. For billions of years afterward, volcanic processes continued to reshape the surface, erupting lava that covered large areas and created the smooth plains we can see in images today. This volcanic material came from deeper in Mercury's interior, from layers that had solidified after the graphite had already floated to the surface. As a result, the volcanic plains are less carbon-rich than the ancient cratered highlands, which preserve more of the original graphite-bearing crust. This relationship between terrain age and carbon content is one of the key pieces of evidence supporting the magma ocean hypothesis. If we can identify which regions of Mercury are oldest and which are youngest, and if we can measure the carbon content in each region, we can test whether the pattern matches what we would expect from the flotation crystallization model. And indeed, Messenger's observations showed exactly the pattern that the hypothesis predicted. There is something deeply satisfying about this kind of scientific confirmation. When observations match predictions in precise and specific ways, it gives us confidence that we are on the right track, that our understanding of Mercury's history is at least approximately correct. Of course, there is always more to learn, always refinements to be made, always new data that might reveal unexpected complexities. But for now, we can rest in the knowledge that the basic outline of Mercury's carbon story is well supported by evidence. As we continue to drift through this cosmic narrative, let us consider what Mercury's carbon tells us about the broader solar system. The presence of carbon in Mercury's original crust means that carbon was available during the planet's formation, that it was present in the materials from which Mercury accreted. This is consistent with what we know about the solar nebula, the cloud of gas and dust that collapsed to form the Sun and planets. That nebula was rich in carbon, in various forms ranging from simple molecules like carbon monoxide to complex organic compounds that form the basis of life. Carbon is everywhere in the universe. It is produced in the cores of stars where nuclear fusion combines lighter elements into heavier ones. When stars die, they spread their carbon throughout space, enriching the interstellar medium with this versatile element. New stars and planets form from this enriched material, incorporating the carbon that previous generations of stars created. In this sense, the carbon on Mercury is recycled stardust, matter that has passed through stellar furnaces and been scattered across the cosmos, before finding its way into the innermost planet of our solar system. This cosmic cycling of carbon connects Mercury to Earth in a profound way. The carbon that makes life possible on our planet has the same origin as the carbon that darkens Mercury's surface. Both came from stars that exploded long before our solar system formed. Both were incorporated into the solar nebula. Both ended up in planets through the processes of accretion and differentiation. The main difference is what happened afterward, how each planet's environment shaped the fate of its carbon inventory. On Earth, carbon has been cycled through rocks, oceans, atmosphere, and living things for billions of years. It forms the backbone of every organic molecule, the structure of every cell, the currency of every metabolic transaction. Carbon-based life has transformed our planet, filling the atmosphere with oxygen, creating soils and sediments rich in organic material, building complex ecosystems that span the globe. Carbon on Earth is active, dynamic, constantly being transformed and transported and recycled. On Mercury, carbon has taken a different path. Without water, without an atmosphere, without life, the carbon on Mercury has remained largely inert, locked in the graphite that coats the surface. It participates in no cycles, feeds no life, drives no chemistry. It simply sits there, absorbing sunlight and re-radiating heat, a passive remnant of the planet's fiery birth. And yet, even in its passivity, Mercury's carbon tells a story. It tells us about conditions in the early solar system, about the materials that were available when planets formed, about the processes that differentiated rocky bodies into cores and mantles and crusts. It tells us about the bombardment history that delivered additional carbon over billions of years. It tells us about the volcanic activity that resurfaced portions of Mercury and buried some of the ancient carbon-rich crust. In its very presence, Mercury's carbon is a record, a chronicle of events spanning the entire history of our solar system. If you are still here with me, still floating somewhere in the gentle space between waking and sleeping, I want to acknowledge your presence and your patience. We have travelled far together already, from the initial question of why Mercury is so dark to the detailed exploration of carbon flotation in primordial magma oceans. We have touched on comets and asteroids, on Messenger's long journey and careful measurements, on the distribution of carbon across Mercury's ancient and volcanic terrains. There is more to explore, more details to consider, more implications to contemplate. But perhaps now would be a good moment to pause and reflect. What have you found most interesting in our journey so far? What images or ideas have stayed with you as we have moved through this cosmic narrative? I would love to hear your thoughts in the comments below. These small exchanges, these moments of shared wonder, help build a community of cosmic explorers, people who find meaning and peace in contemplating the mysteries of the universe. And if you have not yet subscribed to this channel, perhaps now might be a gentle moment to do so. There are many more journeys to take together, many more mysteries to explore, many more nights to fill with peaceful contemplation of the cosmos. Each journey is a little different. Each topic reveals new wonders. And together we can explore the universe one quiet night at a time. Let us continue now, moving deeper into the specifics of how scientists gathered and interpreted the evidence for Mercury's carbon-rich surface. The instruments on Messenger were marvels of engineering designed to operate in one of the harshest environments in the solar system. The spacecraft orbited so close to Mercury that it experienced temperatures that would destroy ordinary electronics, forcing engineers to develop sophisticated thermal control systems that kept the instruments functioning despite the intense heat. The neutron spectrometer, which provided some of the most important evidence for Mercury's carbon, worked by detecting particles that most people never think about. Neutrons are fundamental particles that make up the nuclei of atoms, along with protons. Unlike protons, neutrons have no electric charge, which means they can pass through matter more easily, traveling significant distances before interacting with other atoms. When cosmic rays, the high-energy particles that constantly rain down from space, strike a planet's surface, they knock neutrons out of atomic nuclei. These neutrons then bounce around, colliding with other atoms and gradually losing energy, until they either escape into space or are absorbed by another nucleus. The energy distribution of the neutrons that escape into space depends on what elements are present in the surface. Some elements, like hydrogen and carbon, are very effective at slowing down neutrons, absorbing their energy through multiple collisions. Other elements are less effective, allowing neutrons to retain more of their energy. By measuring how many neutrons of different energies are escaping from the surface, scientists can infer what elements are present and in what quantities. Messenger's neutron spectrometer measured this energy distribution over Mercury's entire surface, building up a global map of neutron emissions that could be interpreted in terms of elemental composition. The results showed clearly that Mercury's surface is different from other rocky bodies we have studied, with higher concentrations of carbon and other volatile elements. This was one of the key pieces of evidence that led scientists to the graphite hypothesis. But neutron spectroscopy was not the only technique used to study Mercury's composition. Messenger also carried X-ray and gamma-ray spectrometers that could detect the characteristic emissions of different elements when they are excited by solar radiation or cosmic rays. These instruments provided complementary information about Mercury's surface chemistry, helping to build a complete picture of what the planet is made of. The X-ray spectrometer measured the fluorescent X-rays emitted when the sun's X-rays strike Mercury's surface and cause atoms there to emit their own X-rays at characteristic energies. Different elements emit X-rays at different energies, so by measuring the spectrum of X-rays coming from the surface, scientists could determine which elements were present. This technique was particularly useful for detecting heavier elements like magnesium, aluminum, silicon, sulfur, and calcium, which make up the bulk of Mercury's rocky surface. The gamma-ray spectrometer worked on similar principles but detected higher energy radiation. When cosmic rays or the sun's charged particles strike Mercury's surface, they can excite atomic nuclei in ways that cause them to emit gamma rays at characteristic energies. By measuring these gamma rays, scientists could detect elements that were difficult or impossible to study with other techniques, including some of the elements that affect the neutron energy distribution. Together, these instruments provided a remarkably detailed picture of Mercury's composition, far more detailed than we had ever achieved before. The data showed that Mercury's surface is indeed depleted in iron compared to what scientists expected, supporting the idea that the planet's large iron core has drawn most of the iron away from the surface layers. The data also showed surprising abundances of volatile elements like sulfur and potassium, elements that were expected to have been lost from a planet so close to the Sun. These findings raise new questions about how Mercury formed and evolved, questions that scientists are still working to answer. But for our purposes tonight, the most important finding was the elevated carbon concentration, the evidence that graphite is present throughout Mercury's surface in quantities sufficient to explain the planet's unusual darkness. This finding transformed our understanding of Mercury, connecting its present appearance to events that occurred billions of years ago and revealing processes that we had not previously appreciated. The confirmation of carbon on Mercury also had implications for our understanding of other planetary bodies. If carbon can survive in the intense environment near the Sun, present in significant quantities on a world that experiences some of the most extreme conditions in the solar system, then perhaps carbon is more widely distributed and more resilient than we had assumed. This has implications for the search for life elsewhere in the universe, for understanding the chemistry of planetary surfaces, and for tracing the origins of organic material in our cosmic neighborhood. As we rest in this knowledge, let us appreciate the patience and precision that went into gathering it. Messenger spent years orbiting Mercury, carefully measuring neutrons and X-rays and gamma rays, building up datasets that required sophisticated analysis to interpret. Scientists on Earth worked with this data, developing models and testing hypotheses, debating interpretations and refining conclusions. The discovery that Mercury's darkness comes from carbon was not a sudden revelation, but a gradual emergence of understanding, a slow crystallization of knowledge from raw data, much like the slow crystallization of graphite from Mercury's ancient magma ocean. There is something appropriate about this parallel, the way the process of understanding mirrors the process being understood. Science is itself a kind of differentiation, a sorting and separating of ideas, with the most successful explanations rising to the top while less successful ones sink out of sight. The truth about Mercury's carbon floated upward through the magma of data and analysis, eventually reaching the surface of our collective understanding where it could be recognized and appreciated. And now, having explored the evidence for Mercury's carbon and the methods used to gather it, we find ourselves ready to consider some of the more specific features on Mercury's surface that tell us about the history and distribution of this carbon. In the craters and plains and mysterious formations called hollows, we can read the story of Mercury's evolution, the ongoing processes that continue to shape this small, dark world. But we will save those explorations for the continuation of our journey. For now, let us simply rest in the wonder of what we have learned, appreciating the progress that has been made and anticipating the discoveries yet to come. Mercury's darkness, once a puzzle, is now a story with characters and plot and setting, a narrative that stretches back to the very beginning of our solar system and continues to unfold in the patient, quiet present. The cosmos is full of such stories, waiting to be discovered and told. Each world has its history, each phenomenon has its explanation, each mystery has its eventual resolution. We are fortunate to live in a time when we can explore these mysteries, when we have the technology and the knowledge to ask questions and find answers that our ancestors could never have imagined. And we are fortunate to be able to share these explorations with each other, to rest together in contemplation of wonders that dwarf our everyday concerns and remind us of our place in something vast and ancient and beautiful. Mercury continues its orbit around the Sun as you listen to these words, tracing the same path it has traced for billions of years. Its dark surface absorbs the sunlight that falls upon it, storing heat during the long day and releasing it during the long night. Somewhere on that surface, in a crater that Messenger photographed years ago, graphite crystals that formed in a primordial magma ocean still rest in the ancient regolith, waiting for no one, serving no purpose, simply existing as they have existed since before life arose on Earth. There is peace in this image, in the recognition that the universe carries on its processes without needing our attention or approval. Mercury does not care whether we understand its darkness or not. It simply orbits, simply rotates, simply absorbs light, and radiates heat in the endless cycle that has defined its existence since the beginning. Our understanding adds nothing to Mercury but adds much to us, giving us context and connection, and the particular kind of joy that comes from comprehending something previously mysterious. As our first major section of exploration draws toward its natural resting point, we find ourselves well prepared for what lies ahead. We understand Mercury's basic nature, its contradictions and extremes, its enormous core and strange magnetic field, its slow rotation and fast orbit. We understand why its surface is so dark, the carbon that coats the ancient crust and absorbs the light that falls upon it. We understand how this carbon came to be there, the flotation of graphite in a primordial magma ocean, the delivery of additional carbon by comets and asteroids over billions of years. And we understand how scientists discovered all of this, the careful measurements and patient analyses that transformed mystery into understanding. What remains is to explore more deeply, to look at specific features and phenomena, to consider the implications and connections, to follow the threads of this story to their natural conclusions. In the craters of Mercury, in the mysterious formations called hollows, in the eternal ice at the poles and the ancient volcanic plains, there are more wonders waiting for us. But those wonders will keep. For now, we can rest in what we have learned, allowing the information to settle and integrate, preparing ourselves for the next phase of our journey. Let your breathing be slow and even. Let your body be heavy and relaxed. Let your mind drift on these cosmic currents, like a leaf on a gentle stream. The universe is vast and old, and there is no hurry. Mercury has been keeping its secrets for billions of years, and it will continue to hold them patiently whether we discover them tonight or tomorrow, or 1,000 years from now. We explore not because the universe needs us to, but because we need to, because something in our nature reaches outward toward understanding, toward connection, toward the particular kind of peace that comes from knowing our place in the cosmic story. You are part of that story, have always been part of it, will always be part of it in some form or another. The carbon in your body is kin to the carbon on Mercury, both products of stellar nuclear synthesis, both participants in the great cycling of matter that has been going on since the universe began. When you contemplate Mercury's darkness, you are contemplating your own ancestry, your own origins, your own deep connection to everything that exists. Rest now in this connection. Rest in the knowledge that you belong here, that you're made of the same stuff as the stars and planets, that your existence is woven into the fabric of the cosmos in ways that science is only beginning to reveal. Rest in the wonder of Mercury's dark surface and the ancient carbon that coats it, a reminder of processes that shaped our solar system and continue to whisper their secrets across the vast distances of space. The journey continues, as all journeys do, but for now there is a natural pause, a moment of rest before the next phase begins. We have come far together, you and I, from the warmth of wherever you are to the sun-scorched surface of the innermost planet. We have explored mysteries and discovered answers, contemplated evidence and marveled at processes. We have been scientists and poets and dreamers, all at once, finding in Mercury's darkness a mirror for our own wonder. When we continue, we will explore more deeply, looking at the specific features that tell Mercury's story in greater detail. We will consider the hollows, those mysterious bright formations that speak of ongoing processes we do not fully understand. We will look at the eternal ice in Mercury's polar craters, water that has survived for billions of years in the shadows of a sun-scorched world. We will contemplate what Mercury teaches us about planetary formation, about the distribution of elements in the early solar system, about our own Earth and its place in the cosmic neighborhood. But all of that is ahead. For now, there is only this moment, this gentle pause between phases, this rest in the wonder of what we have already discovered. Mercury orbits quietly around the Sun, keeping its carbon secrets slowly yielding to our patient investigation. And you, wherever you are, whatever time it is, are part of this great enterprise of understanding, this reaching outward of human curiosity toward the stars. Thank you for being here. Thank you for traveling with me through these cosmic landscapes. Thank you for bringing your attention and your wonder to these mysteries that have waited so long to be explored. In the quiet depths of space, Mercury continues its ancient dance, and we continue ours, exploring and wondering and resting and dreaming, all part of the same vast story of matter becoming aware of itself. The Messenger spacecraft that revealed so much of what we know about Mercury carried not only scientific instruments, but also a capsule containing some of the ashes of the astronomer Clyde Tombaugh, the discoverer of Pluto. These ashes were added to the spacecraft by NASA as a tribute, and when Messenger finally crashed into Mercury's surface, Clyde Tombaugh became the first human to have remains on 2 planets, or rather, on 1 planet and 1 dwarf planet. There is something poetic about this, a reminder that our explorations are human enterprises, carried out by people who lived and died and left their marks on the cosmos in unexpected ways. The crater that Messenger created when it crashed is small, probably only about 60 meters across, but it is there, a new feature on Mercury's ancient surface. In billions of years, that crater will be joined by countless others as meteorites continue to strike Mercury's surface. But for now, it represents the most recent human contact with the innermost planet, the endpoint of a journey that began on Earth and ended in the silent dust of a world 90 million kilometers away. Consider this as you rest, the way our explorations leave traces, the way our questions and our seeking inscribe themselves on distant worlds. We are not passive observers of the universe, but active participants, sending our probes and our ashes and our curiosity outward into the cosmic vastness. Mercury is different now because we have visited it, because we have crashed our spacecraft into its surface and scattered our remains among its ancient rocks. In some small way, we have become part of Mercury, and Mercury has become part of us. This is the nature of exploration, this mutual transformation between the explorer and the explored. We cannot study Mercury without changing it, cannot send spacecraft without leaving debris, cannot ask questions without implying answers, and Mercury cannot be studied without changing us, without transforming our understanding, without revealing truths that shape how we see ourselves and our place in the universe. The carbon that darkens Mercury's surface is a perfect example of this mutual revelation. We did not know it was there until we looked closely, until we sent our instruments to measure and our minds to analyze. But once we knew, we could not unknow, could not return to our previous ignorance. Mercury's darkness became part of our story, a chapter in the ongoing narrative of human understanding, and our understanding became part of Mercury's story, a new phase in the long existence of a world that had circled the sun in silence for billions of years before anyone arose to wonder about it. As we prepare to continue our journey in the next phase of this exploration, let us carry with us the sense of wonder and connection that Mercury's story inspires. We are small creatures on a small planet, but our curiosity is vast, reaching across millions of kilometers to touch worlds we will never physically visit. In this reaching, in this wondering, in this patient accumulation of knowledge, we become more than we were, part of something larger than any individual life could encompass. Mercury's carbon speaks to us across the void, telling us stories of ancient processes and primordial chemistry, and we listen, translating those cosmic whispers into human understanding, finding in the darkness of a distant world illumination for our own wandering minds. This is science at its best, and this is what we celebrate tonight. Here in the quiet space between waking and sleeping, between knowing and wondering, between ourselves and the stars. The journey continues. Mercury awaits. And somewhere in the cosmos, carbon atoms that floated upward through an ocean of molten rock 4.5 billion years ago still rest on the surface of the innermost planet, absorbing sunlight, keeping secrets, waiting for us to understand. Rest now, and when you are ready, we will continue together, exploring more deeply, wondering more fully, finding in Mercury's darkness an endless source of light for our curious minds. The universe is patient, and so are we. There is no hurry, only wonder, only peace, only the gentle unfolding of cosmic mysteries that have waited billions of years for us to discover them. What we have learned about Mercury's carbon opens doorways into questions we might never have thought to ask. How much of the carbon that coated Mercury's primordial surface is still accessible today? Where exactly is it located, and what forms does it take? What other ancient materials might have risen to the surface during that long-ago magma ocean phase? And what might they tell us about conditions in the early solar system? These questions lead us forward, deeper into Mercury's mysteries, toward discoveries that await in the craters and plains and polar regions of this strange dark world. But those discoveries will come in their own time, as we continue our journey together. For now, the important thing is simply to rest in the wonder of what we have already learned, to let the knowledge settle into our minds like graphite settling onto a cooling crust. Mercury is dark because of carbon, and that carbon has been there since the beginning. And this simple fact connects us to processes and timescales that dwarf anything in our everyday experience. In the quiet of your resting place, wherever you are in the world, consider the darkness outside your window, the darkness that falls when the sun sets on our planet. That darkness is nothing compared to the darkness of space, the absolute blackness between the stars where light travels for billions of years without touching anything at all. And yet, even in that darkness, matter exists, swirling and accreting, forming stars and planets, creating worlds like Mercury, where carbon floats upward through magma oceans and coats surfaces in primordial graphite. We're explorers of this darkness, seekers of understanding in a cosmos that reveals its secrets slowly, grudgingly, one careful measurement at a time. Mercury's darkness was a mystery for decades, and now it is a story, a narrative that we can tell and share and contemplate. Other mysteries await, other darknesses to be illuminated by the patient work of science, and we will be there, you and I, wondering and exploring and finding peace in the gradual accumulation of cosmic knowledge. The story of Mercury's carbon is not finished, will never be truly finished, as long as there are questions to ask and observations to make. New missions are being planned, new instruments being designed, new hypotheses being formulated. Bepi Colombo, a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, is currently on its way to Mercury, carrying instruments even more sophisticated than those aboard Messenger. When it arrives, it will add new chapters to the story we have been exploring tonight, refining our understanding and undoubtedly revealing new surprises. But we do not need to wait for Bepi Colombo to appreciate what we already know. Mercury's darkness, explained by carbon from ancient magma oceans and cosmic bombardment, is a story complete in itself, a mystery solved and a wonder revealed. We can rest in this story, finding in it everything we need to contemplate the strangeness and beauty of the cosmos. And so we rest, here at the end of this first major section of our journey, preparing ourselves for the explorations ahead. Mercury orbits quietly around the Sun, its dark surface keeping secrets we have only begun to uncover. Carbon atoms that floated upward through molten rock billions of years ago still wait in the ancient regolith, telling stories to anyone with the patience to listen. And we listen, here in the gentle space between waking and sleeping, finding in Mercury's darkness a mirror for our own wonder. Continue breathing slowly, letting each exhale carry away tension you no longer need. Let your thoughts be soft and wandering, touching on Mercury's dark plains and ancient craters, on graphite floating through magma, on spacecraft journeying across millions of kilometers to gather data and crash into distant surfaces. These images are gifts, offerings from the cosmos to our wandering minds, and we receive them gratefully, holding them gently as we drift toward deeper rest. The journey continues. There is much more to explore, many more wonders to contemplate, many more mysteries to unfold. But for now, we have done well. We have traveled far and learned much. We have connected ourselves to a distant world and found in its darkness reflections of our own cosmic nature. And we have rested in the peace that comes from understanding, from connection, from the recognition that we are part of something vast and ancient and beautiful. Mercury's carbon awaits our further exploration. The hollows and craters and polar ice regions hold stories we have not yet heard. The implications of what we have learned connect to other worlds, other questions, other mysteries that will occupy scientists and dreamers for generations to come. But all of that is ahead, in the continuing unfolding of our cosmic journey. For now, there is only this moment, this rest, this peace. Mercury orbits quietly, and so do we, tracing our own paths through space and time, part of the same great dance of matter and energy that has been going on since the universe began. Rest well, and when you are ready, we will continue together, exploring more deeply, wondering more fully, finding in the darkness of the cosmos an endless source of light. As the first major phase of our journey draws to its natural close, we carry with us the knowledge and wonder we have gathered. Mercury's darkness is no longer just a fact but a story, a narrative woven from magma oceans and carbon chemistry, from spacecraft and spectrometers, from the patient work of scientists and the curious reaching of human minds. This story enriches us, connects us, reminds us of our place in the cosmic tapestry, And the story continues, as all stories do, each ending becoming a new beginning, each conclusion opening into fresh wonder. We will explore Mercury's hollows, those mysterious bright formations that speak of ongoing processes. We will contemplate the ice at Mercury's poles, frozen water that has survived for billions of years in eternal shadow. We will consider what Mercury teaches us about our own world, about the elements that make up our bodies, about the connections that link all matter across the universe. But that is for the continuation of our journey. For now, we rest in what we have learned, appreciating the progress we have made, finding peace in the understanding we have achieved. Mercury's darkness is explained but not exhausted. There is always more to discover, more to wonder about, more to contemplate in the quiet hours of the night. Thank you for being here, for traveling with me, for bringing your curiosity and your wonder to this exploration of cosmic mysteries. The universe is vast and strange and beautiful, and we are privileged to explore it together, one quiet night at a time. Rest well and dream of carbon and starlight, of ancient magma and patient orbits, of all the wonders that await us in the continuing story of Mercury and our place in the cosmos. The darkness of Mercury is not empty but full, not a void but a presence, not an absence of light but an embrace of it. Carbon holds the sunlight that falls upon it, absorbing the energy and transforming it into heat, participating in the great cosmic exchange of radiation and matter that powers all things. In this holding, in this absorption, there is a kind of quiet power, a patience that we might learn from as we contemplate our own lives and our own place in the universe. We hold things too, absorbing the experiences and knowledge that fall upon us, transforming them into understanding and growth. Like Mercury's carbon, we are repositories of cosmic energy, temporary holders of the matter and information that flows through us on its way to other forms and other places. There is peace in recognizing this, in seeing ourselves not as isolated individuals but as participants in a vast and ancient process of cosmic exchange. Rest now in this recognition, in this connection, in this participation. Mercury orbits quietly, holding its carbon, keeping its secrets, waiting for us to return with new questions and new instruments. And we rest quietly, holding our wonder, keeping our curiosity, waiting for the next phase of our journey to begin. The darkness is friendly, the universe is home, and somewhere on the innermost planet, carbon atoms that have been there since before life began continue to absorb light and radiate heat, participants in the same cosmic story that includes us and everything else that exists. This is the peace of Mercury's darkness. This is the wonder of cosmic carbon. This is the rest we find in understanding our place among the stars. And this is where we pause, at a natural resting point in our journey, preparing for the explorations ahead while appreciating the distance we have already travelled. Mercury's darkness is no longer mysterious, but meaningful, no longer puzzling, but profound. And we, having journeyed so far to understand it, are changed by what we have learned, enriched by the connections we have discovered, ready for whatever comes next. Sleep well, and when you wake, Mercury will still be there, orbiting quietly, keeping its carbon secrets, waiting for us to return and continue our exploration. The universe is patient, and so is understanding. There is no hurry, only wonder, only peace, only the gentle unfolding of cosmic stories that have waited billions of years for us to hear them. The journey continues. Rest now, and we will explore more together when you are ready. Mercury's darkness awaits, and so do all the wonders it has yet to reveal. End.